everybody. For this video, we are actually going to calculate the energy of a photon that has a wavelength of 220 nanometers. So if you remember, if you look at the slides, you'll see that a photon is actually a particle of light, sort of particle, but it's a packet of light that has a discernible energy level, right? So clearly, photons that are traveling at a smaller wavelength will have a larger energy, and if they have a longer wavelength, like our radio wavelengths that we did for the other problem, they will have a smaller amount of energy. So let's go ahead and do the first part here, where we calculate the energy of a photon that's traveling with a wavelength of 220 nanometers. So we have this equation introduced to us, E equals H times frequency. So energy is actually going to be in joules, and H, it's actually just a plain old lowercase h, that is Planck's constant, and it will always be 6.626 times 10 to the negative 34 joules times second. So 6.626 times 10 to the negative 34 joules times second. Let's see here. Maybe in the future I'll get some different colored markers, right? But this is clearly something you'd never have to memorize. And then frequency is going to be in per second, which is what we're used to now, which is also the same thing as hertz. So if we have something that is joules times second, and it's multiplied by something per second, the seconds will cancel out and we're left with just joules. So energy of a photon, and let's go ahead and plug it in. Oh wait, the question gives us nanometers and not frequency. So we can't just plug and chug, not just yet. So we hearken back to our other equation that says c, the speed of light, is equal to wavelength times frequency. So if I know the wavelength, which I do, and I know c, which is a constant, I can solve for frequency. So we're basically doing a little side quest here, right, to find the frequency. So c is the speed of light, so we're going to end up having to solve for, our goal is to solve for this, so we're going to have c divided by wavelength equals frequency. So c is always going to be 3.0 times 10 to the 8 meters per second divided by, and if we were to write 220 nanometers in terms of meters, we would have to put 220 times 10 to the negative 9 meters. If you recall, times 10 to the negative 9 is nano. So meters are going to cancel out, and my final unit is going to be per second. So I went ahead and did this little calculation earlier. Are we expecting a big number or a small number? The answer is a very large number, because 220 times 10 to the negative 9 nanometers is like 0.00000, right? 220, and we're dividing 3.0 times 10 to the 8, which is a very large number, by a very small number. So if I multiply this out and I get a large number, I know that I did the problem incorrectly. So you're supposed to expect a large number, and we actually get 1.364 times 10 to the 15 per seconds. So we can take this information and now we can plug it back into this equation, because this is now we figured out the frequency. We already know h, which is Planck's constant, and we multiply everything out and we can get the actual energy of one photon. So to set that up, we have energy equals 6.626 times 10 to the negative 34 joules times second. We have this term times our frequency, which we just found, which was 1.364 times 10 to the 15 per seconds. Right? So we're just multiplying these two together now. What kind of number am I expecting? Well, I'm multiplying something times 10 to the negative 34 times something times 10 to the 15. So it won't be as small as 10 to the negative 34, right? But it's still going to be a small number. So when you type this out in your calculator, again, we should be expecting a fairly small number. So when you type it out, you get 9.04 times 10 to the negative 19 joules. So why would this make sense? A photon does not have a lot of energy. It's just one bit of light, just one. So I'm expecting a fairly small number. However, in part B, and this is something that you are going to encounter, I need to know the energy of 1 mole of photons. So this is the energy for 1 photon, correct? That's what we just solved for. So let me write that out. 9.04 times 10 to the negative 19 joules for every 1 photon. That's really, if I were to put it into a fraction, that's really what we found, right? Joule per photon. But I need to know how much energy I'm going to get if I have a mole of photons. So you thought you were done with Avogadro? Nope, surprise, he comes up, he's going to keep coming up again. So if we all know it's 6.022, so we have 6.022 times 10 to the 23rd photons for every 1 mole of photons. Right? So photons are going to cancel out, and when I multiply these two numbers, I'm going to get the energy that is contained within 1 mole of photons. So what kind of number am I expecting? Well, I'm multiplying times 10 to the negative 19 times 10 to the 23rd, so I'm expecting a number that is kind of big, but not insanely large. So if you type this out in your calculator, you should get 5.44 times 10 to the 5, and what is our units? Joules per mole. Ran out of room there. Okay, all right, I hope this helped, and I'm told to say smash that like button.